So now we'll go into how to compute actual derivatives for functions that are more complicated than the original power function that we started with. In particular, we'll look at how we can, in a sort of fast way, compute sums of different functions, or the derivatives, of course, of sums of different functions, but also products of functions. So what happens if I multiply two functions and want to take the derivative of that product? Same way with quotients, so dividing two functions. And we'll have a look at the chain rule, which operates, which we'll use on for composite functions. So sums and differences, that's the easiest part. So if we have two functions, let them be f and g, two differentiable functions, well, we might be interested in, well, if we have these two functions, add them up to get a new functions called here capital F. So capital F might be the sum of f and g, so f plus g. Can we actually then say something immediately about the derivative of this capital F? And the answer is yes, simple. That's simple. It's just adding up the derivatives of f and g. So let's look at this example over here, and let me do that on paper again. So the example here is we have this function which is defined to be 5 times x to the power 6 plus 2 divided by x to the power 100. That's a function which is the sum of two power functions that you already know, and we're interested in taking the derivative of this function. So what do we need to do? Well, we actually need to take the derivative of these two separate functions separately. So this is going to be, well, first step, let's just rephrase the second part here as in a way that makes it more clear that it is actually a power function, because this is exactly the same as saying this is 5 times x to the 6 plus 2 times x to the power minus 100, right? So x to the minus 100 is the same as 1 divided by x to the power 100, if you remember. So now we can do the computation, because we have to take the derivative of the first bit, and then we have to add that to the derivative of the second bit. So the derivative of the first bit is going to be 5 times 6, the 6 coming down, x to the power, and we reduce the power by 1, so 6 becoming 5. That's the first bit. The second part here is 2 times, well, derivative of x to the power minus 100. We follow the same recipe. So minus 100 comes down, so we multiply this by minus 100. And then we have to reduce minus 100 by 1, so that gives us minus 101. And now we're there, because what is this? It's just 30 times x to the power 5 minus 2 times minus 100 is minus 200 times x to the power minus 101. And that's the derivative. So just adding up the two separate derivatives. So we can see that here again on the slide. So here's the same step. So we rewrote this 2 divided by x to the power 100 as 2 times x to the power minus 100. Then we took those two derivatives, and indeed in the last line compared to what I just wrote down, again you see that this x to the minus 101 is rewritten as 1 divided by x to the power 101, which is actually the same. So that is an optional final step. So that's what happens with sums and also with differences of functions. Just look at the two separate components and take the derivatives of each of these components. So then let's look at the product of functions. So what happens if we multiply those two functions f and g? So now the capital F, the big F, is a function which is a product of little f and little g, so f times g. Now the product rule says it's a bit more complicated than what we just saw. So the derivative of this product of capital F, big F prime, equals, well, the derivative of the little f times g itself plus f itself times the derivative of this function g prime. So you just have to learn this by heart, I guess, but let's look at an example to see how it works in practice. And let me again do this example on paper, and then later on we can compare this with a slide. So we have this function h, which is a product of two functions. It's it's given as a function of t, not of x, but that should not matter to us. So h of t is this particular function, t to the third minus t, times the second function, namely 5t to the fourth plus t squared. So let's call this first function f of t, and this second function g of t, and we have a product. So h is a product of f and g, and now we can use this product rule, which says, well, then the derivative of h prime is going to be the derivative of f prime t times g itself plus, well, the reverse essentially, f of t times g prime t. Okay, so that's what we have to do. So let's do that then. So h prime of t, if this is f, well, first thing we need to do is compute f prime. So if this t to the third minus t, we call it f. So let's take the derivative of that. What is that? T to the third gives us 3t squared minus 1. So here we actually use the sum rule, right? So f itself is the sum, or the difference of t to the third and t. So we can sort of take the derivatives of each of these parts. So this is f prime. We have to multiply f prime by the original g, which is the bit in these brackets. So we multiply this by 5 times t to the fourth plus t squared, first part, plus the second part. Take now f itself, which is this t to the third minus t, and we multiply it by the derivative of this function g over here. So what's this derivative? Well, it's 5 times 4 times t to the third, so 20 t to the third. So I'm reducing the power by 1 here, and this one's even simpler. It's 2t. So this second bit is of course g prime. This g prime here, the derivative of this bit. We multiply it by f itself. So now this essentially this already is it, but we can work this out to simplify it a bit, and to take like terms, collect like terms. So let's get rid actually of all the brackets in this expression. So what would we get? Well, this first part gives us t squared times t4, a t to the sixth term, where the coefficient is 3 times 5, so it's 15 times t to the 6. Then we have 2t to the 4 terms, so we have 3t squared times t squared, so that's 3t to the 4th minus 1 times 5 times t to the 4th, so 3t to the 4th minus 5t to the 4th, that's minus 2t to the power 4. And then we have a t squared term, which is the minus 1 times t squared. So this is minus t squared. That's the first expression. Now here, likewise, in the second part, we can get rid of brackets. So again, I want t to the sixth term, so t to the third times 20 t to the third, that makes 20 t to the sixth. Then we have t to the fourth terms, then we have t to the third times 2t gives us 2 times t to the fourth, and minus t times 20t to the third gives us minus 20 times t to the third. So we have 2 minus 20 times t to the fourth, or minus 18 times t to the fourth. So that collects all the resulting powers t to the power 4. And finally we have a t squared term, namely if you multiply minus t over here with 2t over here, we get minus 2t squared. Almost done, because now we have these 6 different terms, but you see here the 2t to the 6 terms, we have the t to the 4 terms, and we have the t squared terms. So let's collect those just to make the expression a bit simpler. So we have 15t to the 6 plus 20t to the 6, that is going to be 35 times t to the 6 minus t to the 4th minus 18t to the 4th is going to be minus 20 t to the 4th, and finally minus t squared minus 2t squared is minus 3t squared. So this is the end result of computing h prime t. So here we saw, of course, that h was this product, and we'll be given names, these factors f and g, and we computed the derivatives of f and the derivative of g separately, and plug that into the product rule, and then we simplify the expression. That's how it works easiest usually. I might add to that, what you could have done here is first get rid of these brackets. You would just have a simple adding up of a couple of normal power terms. So first do the product essentially here, and then taking the derivative, you would have got the same answer. So you can actually try this for yourself. Okay, so let's get back to the slide. So here indeed it is. So we had this f and the g that I just mentioned, which f times g makes up h. We had this product rule, we had the derivatives of f and g called f prime and g prime, and we plug those into this product rule expression, simplify the resulting equation into the resulting expression into the final expression that you see in the bottom row over here, which is indeed the same as what we did on paper. So this is how differentiation of a product of functions goes. Let's next have a look at a quotient, so division of two functions. So if indeed capital F, again our function big F, is now defined to be the quotient of little f and little g, so f divided by g, we also would like to be able to take the derivative of that quotient, and for that we have the quotient rule, which again you unfortunately have to learn by heart or look it up, but that's sort of a waste of time because it's not that much work, I guess, to put this in your mind. So big F prime, the derivative of this quotient, is then given in terms of its constituents. Little f prime times g in the numerator minus f times g prime. So this looks a lot like the product rule, but with a minus sign over here. But you also have to divide it now by the square of this denominator g. So we have to divide it by g squared. So it's easiest to see this at work in an example again. So we're going to look at this particular example, which is the quotient of the function f, x squared minus 1, divided by a function g, which is 2x squared plus 1. And we're going to use the quotient rule on that particular expression. So let's have a look again at the paper. So we have this function big F, which is x squared minus 1 divided by 2x squared plus 1. And we are interested in taking the derivative, which we could have written with a dx kind of notation, but also with this prime notation, if you remember. Same thing. And we see this as a quotient, right? So let's define it to be fx divided by gx prime. So with fx, the numerator, gx, the denominator. And well, let me write down just for remembering what it is, what the quotient rule looks like. So it's just f prime x times gx minus fx times g prime x. That's going to be the numerator. So here we have the derivative on f times g itself minus f times the derivative of g. And we then have to divide that not by g, but by g squared, the square of the function g. So this is what we need to know. So let's compute that. Do that here. So what do we need to do? So f is x squared minus 1, is the numerator. So let's take the derivative of x squared minus 1. Well, that's just 2x, right? So in the first bit, this f prime over here is just going to be 2x, and you have to multiply it by g of x. Multiply it by 2x squared plus 1. And then we take minus f itself. So f was x squared minus 1. We have to multiply that by g prime. So the derivative of this denominator, so the derivative of 2x squared plus 1, well, this 1 drops out if you take the derivative, so we just get 4x, so times 4x. That's the numerator of our quotient formula, and we have to divide this by g squared. So g is this thing. I have to take the square. Okay. Now, essentially this is it, but we can still make the expression look a bit easier on the eyes. How do you do that? Well, just get rid of the brackets, in particular the brackets in the numerator. So what do we have here? 2x times 2x squared, that makes 4 times x cubed. 2x times plus 1, that makes plus 2x. And we have minus x squared times 4x, gives us minus 4x to the power 3. And then we have minus, do not forget this minus in front here, times minus 1 times 4x. So 2 minuses here, minus times minus 1 times 4x, so it makes plus 4x. And we divide this by 2x plus 1 squared, which we leave at this as it is because it's already nicely factorized. And finally that numerator here simplifies because, as you can see, the 4x cubed over here is cancelled against this minus 4x cubed over here. And 2x plus 4x together make 6x. So this is the derivative of this particular function here, which was the quotient of the top x squared minus 1 divided by the bottom 2x squared plus 1. And we used the quotient rule as we had it on the slide, and I reproduce it here on paper. So this is the result. Let's get back. So here we are. So we had this f, which was the numerator, the x squared minus 1. And we had the g, which was the 2x squared plus 1, the denominator of this expression. Well, yeah, we sort of separately already pre-compute what these derivatives of those two functions are. F prime is just 2x, G prime is 4x, and then we can actually compute what the derivative of this quotient is by using the quotient formula, which is reproduced over here, and plugging in the expressions that we have on top. We find the next line and simplifying that next line, because x cubed term turn out to drop out here out of the numerator. We have left the 6x. The numerator divided by g squared, or 2x squared plus 1 within brackets squared. Okay, so try at home your abilities here, your understanding, by looking at different function. Capital F is square root of x minus 2 divided by square root of x plus 1. So again, those are two functions, f, you might call them again f and g. Use them, plug them in the quotient formula and see what you get, and then you can compare. Actually, at the end of this pack of slides, of this slideshow, there is a worked example of this exercise, so you can compare with what you got. So please do that at home to just see whether it works for you. So the final part that I'd like to do in the rules basically for making differentiation possible or easier is the chain rule, and the chain rule applies to functions which are composite functions. So what's a composite function? A composite function essentially is a function which is, first we do one type of operation, so we apply one function, and then to the result that we get from doing that first function, we put that into a new function, a second function, and the end result is the composite function. So here's an example. So here's the function y equals 2 minus x squared, and that to the power 3. So if you see such a function, what would you do if I were to ask you, can you compute, say, what happens, how big is y if you plug in x equals 1? Well, what would you do? Well, probably you would first compute, well, what's 2 minus x squared, so in this case 2 minus 1 squared, and that result you would raise to the power 3. So you first apply the first function 2 minus x squared, and to the end result of that function you'd apply the second function, which in this case just is raising to the power 3. So a different way of saying this is, well, we actually add one sort of intermediate variable, so let's call it this intermediate variable u. So u is the result of applying the first function 2 minus x squared, and then y is actually gotten by applying the second function, namely raising to the power 3, applying that to that result u. So y equals u to the power 3. So together these two functions actually define what this original function was. And the different way of saying this is, well, I define y as the composite of two functions like so. We apply first a function g to x, where g is this 2 minus x squared. So we first compute the function g on x, or in other words, we compute 2 minus x squared. And then the result of that, we plug into the second function f, where this function f is just a cubic function, raising something to the power 3. So if I plug in x into f, it gives me x to the power 3. If I plug in g, or in other words 2 minus x squared into f, it will give me 2 minus x squared to the power 3, precisely what we wanted. So this is the sort of functional notation of this same composite function. We actually have names for those, for referring to those. This function which we have to apply first, so in our case 2 minus x squared, which I call here g, that we call the interior function, the thing which you do first. And then on the outside, the result of that thing, we have this function f, which is raising to the power 3. We call that thing the exterior function. So this is a common notation, f applied to g of x. Different notation that's also sometimes used by mathematicians is f with this little circle g, and it's pronounced f after g of x. So you first apply G and then F. That's basically what it means, since mathematicians, as you know, read from right to left. So we are interested in a function that's a composite function, and we would like to know what is the derivative of that composite function. So here we have this function k of x, which will be the composite of a function f and a function g. So in terms of this variable-oriented notation, we would define an outcome u of the first function or the interior function, and then apply the function f to that outcome to get our y. Well, then what does the chain rule say? Well, if the function k is this composite, then the derivative of k, or dy, because y is the outcome of k, by dx, derivative of y over x, we can write this as du dx multiplied by dy du. So that's one way of writing. If we rather use this function-oriented notation, so in terms of just the functions f and g, so kx is first apply the function g to x, and to that outcome plug that into f, the argument of f, so f of g of x. That's the function k of x. In that case, the derivative of k, or k prime, is given by the chain rule as being the derivative of this interior function, g prime, multiplied by the derivative of the exterior function, f prime, evaluated at g of x, so with plugging in g of x as its argument. So let's see again how this works for our example. So let me do that on paper again. So let's go to the paper. So we had this function k of x. It was 2 minus x squared, the interior function, and that outcome raised to the power 3. And we wrote this as the function f, the cube function, applied to the function g of x, which was this 2 minus x squared. So in other words, f of x would be x cubed, and g of x would be 2 minus x squared. Now we are interested in the derivative of k, in other words, k prime of x. Well, by the chain rule, how do we compute this in general? Well, we have the derivative of the exterior function, the f function, evaluated at g of x, multiplied by the derivative of the interior function, this function g. That's the chain rule. So we have to do that. So how do we go about doing that thing? What's f prime? Well, if f itself is x to the power 3, f prime of x would be 3x squared. Here we are actually not interested in f evaluated at x, but f evaluated at g of x. So instead of having, write it here, f prime of x would be 3 of x squared, 3 times x squared, and g prime of x equals minus 2x. So here we're interested in not 3 times x squared, but 3 times g of x squared, or in other words, 3 times 2 minus x squared, because that's what g is, right? Squared. So plugging in where we see the x is over here, the function g of x, we get this part for the first component, the first factor in this product. And we have to multiply this by the derivative of g, of the interior function, and that was minus 2x. So we just evaluate that and x, so times minus 2x. Well, this is it, except that we can do this multiplication and see that 3 times minus 2 is minus 6 times this x times 2 minus x squared, which is a nicely factorized form. So this is k prime of x using the chain rule. So let's see that happening again on the slide. So we have k of x is 2 minus x squared to the power 3. So the exterior function is this cube. We cube the function gx, the function 2 minus x squared, which is over here. And we use the chain rule then to determine the derivative of the resulting function kx. So k prime of x is f prime evaluated at g of x times g prime of x. F prime of g of x was 3 times 2 minus x squared times g prime of x minus 2x, so times minus 2x. And together that gives us minus 6. 3 times minus 2 is minus 6 times this x times the 2 minus x squared. So the result is indeed minus 6x times 2 minus x squared. So this is the function-oriented approach. Let's also, and you can yourself try and get the same result if you use this variable-oriented approach. Let's take a second example. So let me again do this on paper. So k of x is going to be 5 times x to the power 5 minus 11 times x to the power 3. And that result we are going to raise to the power 4. So the exterior function is this raising to the power 4. So we might say the f of x, the exterior function is x to the power 4. We can compute easily now what the derivative of f is. That's 4 times x cubed. And the interior function, so the stuff that we will do first, is going to be called g of x, and that's 5 times x to the 5 minus 11 x cubed. And again, we can compute the derivative of that function as 25 x to the 4th minus 33 x squared. So we're going to now compute the derivative over here. K prime is going to be the derivative of f, 4 times x cubed, and now not evaluated at x, but every position we see the x, we just put in the g of x. So it's 4 times g of x, this object here in brackets, to the power 3. That's f prime of g of x. And we multiply this by g prime of x, which is 25 x to the 4th minus 33 squared. So let's do that on paper just to see that once again. So here we are. K of x equals 5 x to the 5 minus 11 x to the power 3. And that resulting output will be raised to the power 4. So what's the k prime of x? The exterior function is 4, this thing to the power 4. Something to the power 4, we have to take the derivative of that and plug in the stuff that's it's operating on, the interior function. So it gives us 4 times that stuff to the power 3. And we multiply it by g prime. So what's g prime? It's 5 times x to the 5 derivative, so it's going to be 25 x to the 4th from this first term over here, minus 33 x squared. So can we simplify that a bit? Well, I'd like to keep this power over here the way it already is, because it's already a nice, almost nicely factorized form. But let me just operate a 4 on the 25. So we get 100 times x to the 4th minus 132 x squared times 5x to the 5 minus 11x power 3 to the power 3. And if we want to really, well, let's do that actually. If we want to really factorize this, we take out the powers of x that are in common here. So we see an x to the 4th and an x squared. So let's take those out. First bit gives me x squared times 100x squared, because x squared times 100x squared would give us the 100 times x to the power 4 minus 132, because it's x squared times minus 132 would give us the minus 132 squared. And likewise here we can take out the x to the power 3, but be careful, we're raising this whole thing to the power 3, so we also have to raise the x cubed we are taking out here to the power 3 times what's left. If I take out x to the power 3, this becomes 5x squared is what's left, and there's a minus 11 remaining over here, and still we have the power 3 over here as well. So collecting the x's here actually, x squared times x to the power 3 to the power 3. So a power to a power is just x to the power times this power, right? So x to the power 9. So it's x squared times x to the power 9 gives us x to the power 11 times 100 x squared minus 132 times 5x squared minus 11 to the power 3. So this is just a different way again of writing. So let's go back to the slide then. And indeed, actually on the slide we just left it at this particular point. So it gets us where we want to be, and you can simplify it a bit by taking out the powers of x which are common across these various terms. Okay, so that's the chain rule. So a second example of the chain rule in operation. Again, try to practice with this. I'd advise with the exercises, also the exercises from the book. Some of which will be done by Jeline in the videos on the tutorial, and you can, of course, if you have, this is something you have to do a lot of times to actually internalize for yourself the workings of, what's the product rule again, what's the quotient rule again, what's the chain rule again. First time, it's sort of, you're likely to have to look these up a lot of the times, but if you have practiced them all a number of times, a sufficient number of times, they should sort of start to become more routine, and that's where you want to be after you've finished this course. So that's essentially the end. So in the slide there's still an appendix with this at-home exercise that I gave you on this quotient rule. So try this for yourself, and then have a look at the computation of that derivative of a quotient. See you next time.